We're the praying Prions, and this is our bio-inspired octopus hand. Our objective was to determine how an octopus's flexibility could be applied to a bio-inspired hand. Through our discovery decomposition, we read an article about an octopus, and we found that octopus have four main moving techniques, which include bending, torsion, elongation, and shortening. And these accumulated to about over 16,000 distinct combinations and events for an octopus's tentacle.
When developing an analogy for the octopus limb, we found it difficult to find many similarities. However, we were mainly focused on the performance criteria. This is because our hand is focused on increasing mobility and degrees of freedom of the current prosthetic hand. And with this, we can better mimic the octopi's over 16,000 arm deformations.
With that research there, we had the goal of improving the human finger by increasing the degree of freedom on a human hand.
So for our initial designs, we came up with two different solutions. One was an expanding scissor hand, which only allowed movement in one mobility direction, and the other was a ball and socket joint. And we were worried about the stability of this. Our first design was very loosely based on an octopus arm, and we also used a ball and socket method for this. We also came up with ideas that were closer to finger joints. We came up with ideas that could stack onto each other. And we also decided on the string in the center groove. We mixed and matched and combined these and prototyped and combined these to finally do our main design.
The linkages and most of the components, we 3D printed them using the PLA material. The middle core of the fingers was 3D printed using Ninja Flex material, which is a thermoplastic urethane. To pull the fingers for the mechanism, we use the fishing wire. To give the support to the prosthetic hand, we use a wooden structure. And to the wooden structure, we use a rack and pinion tuning gear. To fix various linkages, we use the super glue, and we use the rubber bands to connect the joints together.
Here is a presentation of our final design architecture and some of the overall sizing that we have for our prosthetic hand. As you can see on the on the left, that we integrated our fingers onto the original Phoenix design, and you can see that the average size of the fingers is definitely longer than a human hand. And we incorporated that idea to see and test around with the increased mobility in the different reaches that the fingers can get to with regard to the longer fingers. In addition, on the right picture, you can see some of the hard shell pieces that we use around our soft inner core. And you can see in that picture that we have 4 grooves running along that piece, and those grooves act as alignment features for our pull wires so that we can pull consistently along the 4 major directions that we wanted each finger to actuate upon.
This is an example of how our design does 360 degrees of movement. This is also us showing 4 cardinal directions that we can do.
In addition, in order to compare our design with the original Phoenix hand to sort of see the difference that we incorporated within our design, we took some side-by-side photos of each of the designs. As you can see in this first photo, both hands managed to pull off the same curl with respect to the fingers curling to the palm. This image demonstrates that the flexibility of the materials does match with the original hand. We can see that compared to the original Phoenix hand, due to the flexible nature of our fingers can pull off very complex and different configurations with respect to the individual fingers themselves. As you can see, our index finger can actually pull in the opposite direction the normal finger could pull in. We can see that because of these different degrees of freedom we can pull off with the fingers, we can possibly have or we could possibly create some very imaginative grasping techniques. Some possible future uses that we can do with our hand is that we can increase the ability for humans to grasp and carry objects in multiple directions because of the flexible nature of the robotic fingers. In addition, this initial prototype could act as a start to investigating different soft materials that could be used in prosthetic hands to sort of get a more natural actuation within the current existing prosthetic hands. And the overall design itself demonstrates that it is possible to develop fingers that have complex movements.
Some future improvements that we noted during the design process was to first make the inner core more flexible. This would allow for easier actuation and deformation of the finger. Further increasing the reach or length of the finger would provide easier grasping, and increasing the joint flexibility would also contribute to the ease of actuation. A fully controlled servo platform would be desired for manufacturing to promote ease of use for the end user. Why is the Octo hand better than all other hands, one might ask? It comes down to simplicity, manufacturability, and improvements over currently available hands. Our simple design lends well to easy prototyping and quick and efficient mass manufacturing using injection molding machines. This would further reduce the costs for higher production volumes. However, most importantly, our hand improves the capability and experience by increasing the overall dexterity of a prosthetic hand without forfeiting any of the necessary stability for everyday use.